we are going to do things fairly similar to the QPE lecture yesterday. So for the Grover search algorithm, what we are going to be going through firstly the theory behind Grover search. We are going to do a little bit of a hands-on, and then we're going to start talking about the applications of the Grover search. I'm going to probably rush through certain parts. I'm going to cut short certain parts of it. I think particularly for the hands-on and the applications of Grover search. But yeah, feel free to ask questions because I want there to be enough time for questions and enough time to go through the theory because I think these are important concepts to remember. But yeah, please feel free to. But that again, I want this to be as interactive as possible. Feel free to type anything to the chat if there's anything you don't understand. Okay. Okay. So first, the theory behind Grover's algorithm. I'm going to start with the intuition of Grover's search because I just want to I want to start motivating it first in kind of layman's terms before jumping into the dirty mathematical details. So the Grover search algorithm is really motivated by this thing that we call the unstructured search problem. And what the unstructured search problem is, suppose that we have a database of objects. This database of objects is unsorted, is unstructured. There is no particular structure. It's just randomly placed everywhere and placed in like your in your database. And we have specifications for a specific object within that database. Our job is to find what the problem that we want to solve is that we want to find the specific object within the database. Okay. So how would we normally solve something like this? What we will do is that because it's an unstructured search problem, what we'll do is we'll just go up to the first object, we'll check it to see whether it's that we'll see whether it has the specifications. If it does, all good. If it doesn't, we move on to the second object. If it does, it doesn't. If it does, then we'll go through it again. If it does, then all good. If it's not, if it doesn't fit the specification, then we'll just move on to the third. And so I hope that you can see that in the worst case scenario, you will have to search through the entire database. Can everyone see that? So thumbs up if you understand what I've just said. Okay. Yeah. Okay. I see some thumbs up. I see some thumbs up here and there. Okay. Yeah. Okay. Okay. Great. Okay. So yeah. So this unstructured search problem is it's pretty clear that the worst case complexity in this case, if we have a database of n objects, the worst case complexity for it is O(n). Okay. Now, what now from the intuition, we are going to move into how we define the database of objects and the specifications for these objects for the specifications for the specific object. So for the database of objects, we are going to pretend that we're not going to we are going to represent it in this idea that we have a domain of n numbers. For simplicity's sake, because we're working in the binary system, we're going to assume that n is the power of 2. And that big N is the power of 2, and that any integer can be represented in its binary form, which means that we'll need small n qubits. So if n is to the 2 power of small n, we're only going small n qubits. or bits for that matter, actually. You can represent things, if you represent things in binary from you are really, for any of these numbers, you can represent it in small n number of bits rather than big N, if n equals to 2 to the power of small n. Okay. For the specifications of for a specific object, we are going to have a function that checks whether the object in the database fulfills those specifications. What that means is that we are going to have a function f, that takes in anything from the database and outputs 0 or 1. What does this 0 and 1 mean? You still remember when I went through kind of the history of quantum computing and important concepts. When we started out with the bit, what happened was kind of like it could be on and off, or it could be Boolean, where it could be either true or false. And so in this case, 0 and 1, fx equals to 1 if it fulfills the specification, so that means it's fx equals to true if x fulfills the specifications, and fx equals to 0 if x doesn't fulfill that specifications. Okay. Any questions about these two parts of the problem statement? About database objects and the specifications? Okay. Okay, I'm going to move on. If you have any questions, just please type it. I will take it. If you're taking a while to type it, I will answer it as we go on. Okay, so now instead of the intuition that we had, I can now translate it into this problem, which is, suppose that we have this certain function. This function, which means that suppose we have this specification where for a particular fx, it will be 1, but we don't know what that x is. So to translate it into the terms that I put it previously, the database of objects is the domain, is from the 0 to n-1. The specific object to be searched for is x, and the criterion will be f. Okay. Does this x where fx equals 1 have to be unique? Okay, so for this particular problem, I'm going to say for now I'm going to say yes. Grover search can be used. Grover search in this particular algorithm, for the Grover search algorithm I'm going to go through, is specifically if x is unique. There are ways to change it such that x isn't unique. It's unique, and so you can have many objects that fulfill this particular specifications. These come with like kind of changes to the mathematics. Although you can still prove stuff in the resource estimation that it still fulfills the same worst case complexity. But I think for simplicity sakes, let's just assume it's unique in this point. At this point, going from the unique problem to the non-unique problem is actually pretty simple, and going through the going through the unique solution is actually simpler to start with. Okay, so yeah, so that's a good point to bring up. Yeah, we are assuming it's unique. There are ways you can go up and make sure that it's not unique. There are ways to change this problem to fulfill the non-unique options. Okay. Okay, so the pieces of the puzzle, we are going to apply this on the quantum computer. We are going to need to assume that we can perform the function f, and this implements this function, and we can implement this function in quantum circuits. As I will be going through later, this is a non-trivial problem. This function f will be implemented as the oracle. in Oracle. And we previously learned how to implement the Oracle while going through the Dutch Joza algorithm, the Dutch algorithm, the Dutch Joza algorithm. And this is actually why I decided to go through the phase kickback this morning as well, because the Oracle precisely uses phase kickback in order to implement it most of the time. So there are certain cases where you don't need phase kickback for the Oracle, but most of the time you will need the phase kickback. Okay. So to kind of jump into the straight high level vision of the grower circuit, we can see that it will happen again in two workspaces. One, the first register, the first n qubits. As I said, this is the part that we're similar to QPE. This is the part we're interested in. And the second part is the Oracle workspace. Note that although that everything has 4 lines over here, this doesn't mean that this is limited to 4 qubits. This is just a way of saying this can take as many or as little qubits as it needs. And so to perform the function f, we can actually just to perform the function f, sometimes that will require the Oracle workspace, basically, to convert the function f into the Oracle. Okay. So this is the Grover circuit. It's actually made up of just two parts. First is the Hadamard gate. Okay, we only care about the first n qubits. I think I just went through that. We only care about the first register. The second part is the Hadamard gates, where we get the uniform first. Is the H with the superscript a representation of unitary for a multiple qubit Hadamard gate? No, it's basically what you are doing is basically you're just applying the Hadamard gate to every single qubit. So what that would look like is basically, you remember how for the phase kickback recap that I did this morning for the 2 qubits, I just applied Hadamard to the first qubit and Hadamard to the second qubit. So you're just applying Hadamard to every qubit over here. Okay, yeah. Great. And that's a good question to ask if you think. And so this up to this point, this is things have been pretty standard. And so the crux of the algorithm really lies in this part, G, which you can see that we just apply multiple times over here. And we do this, and in particular, we do this O(n) square root times over here. And so this is where the quadratic speed up for Grover's algorithm that you often hear about comes from. It's because you still remember when I motivated the problem, when I started talking about unstructured search problem earlier, we said that the worst case complexity is O(n). You have to just go through it one by one and hope for the best that you will see that you will get it. That you will get the that you will find that object on like the first try, the second try, third try, but in the worst case, you have to search through the entire thing before you get it. For the Grover search algorithm, we just need to implement this Grover iterator O(n) square root times. And so we kind of discard the constant function, the constant in front of it, and so this is where this speed up comes from. Okay, so now we are going to take a further deeper look into the Grover iterator. The Grover iterator really comes in this form, where you have an oracle, where you have oracle that can perform this function, where for that particular object that you're looking for, it can perform this -1 to the power of fx over here. And this is basically just applied changing the phase for the x that you want. We've learned we saw how one might build something like this. How one might build something like this for the phase kickback. I'm going to just put it out there right now. I'm not going to particularly be going through ways to build the oracle right now, because that's quite a big area of research. And there are many schools of thought on this, but phase kickback is particularly necessary for most of these schools of thoughts. Okay, so that's the oracle. And so the intuition behind what oracle does is basically because what we're doing is we are going to flip the state that we want to find. The intuition of why we want to do this is so that we can isolate the correct state, isolate the state that we want to find. What we want to do after that, after isolating that correct state, because now everything else is in 1, everything else is in plus, only the ones that is the one that we find has a phase of minus. And doing that, what we can do is that we can use the Grover diffusion operator, this part over here, to increase the amplitude of the isolated state. What happens when we increase the amplitude of the isolated state? It means that the amplitude of the other states are reduced. And so the probability of measuring the isolated state increases. Okay. So can everyone see that? Yeah. Okay. So can everyone see the intuition behind what the Grover iteration circuit does? So if I were to go back here, the crux of the algorithm is a Grover iterator. Each Grover iterator, what it first does is we isolate the correct state we want to find, and then we increase the amplitude of the isolated state. We apply it a second time to increase the amplitude of the isolated state, and then we increase it, and we increase it, and we increase it, and we increase it until it's at its highest point. The reason why we stop at O square root n is because there's an optimum value for it. There's an optimum value for the number of Grover iterators you should put, which I'll be going through later. But can everyone understand the intuition of why of the Grover iteration circuit here? Okay. Thumbs up if you understand. If you don't understand, please ask a question, please, or you can just put. Yeah. Okay. I see a few thumbs up. Okay, I'm just going, in the interest of time, I'm going to move on. If you have any questions, please just ask. Yeah. Okay. So yeah. Okay, so now we are going to go through what happens in one Grover iteration, just so that you can kind of see what happens. So I just explained the intuition behind it. Now we are actually going to do the mathematics in order to solve it. Okay. So suppose the good state, the state that we want is G. Okay, I should have probably used X again because that's what I started out with, but I've created my slides. But that's probably so. G stands for good state, while the rest of the states are B over here. So we don't really care about what the other states are. We only care that G is as high as possible. So G and B are very creatively named, GCat and BCat are just very creatively named after good and bad over here. So the good state is 1 over n, or 1 over square root n over here with G. and this is the current amplitude, and for all the rest of the states, the bad states is just the corresponding like square root n minus 1 over square root n. What we're going to do now is we are going to perform quite a useful transformation where we are going to let cosine theta over 2 equals to the amplitude of the bad states, and sine theta over 2 equals to the amplitude of 1 over square root n. I hope that you can see that we can do this because if you realize that these are probability at the end of the day, these are probability amplitudes. And so what happens is that the square of the amplitudes over here have to all add up to 1. You see, for the good states, this is, if we square it, is 1 over n. If we square the bad states, it's n minus 1 over n. You add them together, it's 1. For cosine theta and sine theta, we can just, this can be done pretty easily. This transformation can be done because cosine square plus sine square equals 1. This is a very useful trigonomic transformation that I think many of you have probably gone through in school before. And so what this converts to in the end, so what psi converts to the uniform position of states that which defined as psi over here, what happens is that we can then change it into sine theta good states and good state and cosine theta over 2 bad states. Okay. Any questions about this part? Okay. I don't see any questions. Just feel free to type any questions. Okay, the reason why we wanted to do this is so that we can represent things in the graph. And so what happened, and the graph representation just makes this a lot simpler to understand what happens. Okay, so what happens, okay, so now we start in psi, which is currently the uniform superposition of states over here. And we can represent it into this graph over here, on the right. Now, we first apply the oracle. What does the oracle do? Can anyone tell me what the oracle does again? Mark the good state. How does it mark the good state? Yes, it flips the face. So first thing we do when we apply the oracle over here is to flip the state. So we apply the oracle to the uniform superposition of states. We just put a minus behind it, and using the trigonomic identity, we can move things in. Move it into the sign. Okay. So pretty simple stuff, I hope. Please. The next thing we do is we want to apply the Grover diffusion operator. What does the Grover diffusion operator does? So the second part of the Grover iterator circuit, what does it do? What's the intuition behind it? We want to amplify the good state. And right now, what we have is we have isolated the good state now. We have isolated the good state because the phase is now different from the rest of it. And so how we increase the amplitude of the isolated state over here in this Grover iterator, is by flipping it over by reflecting it over the uniform superposition of states over here. And so if you perform you see the circuit here is made up of Hadamard gates. There's a Hadamard over everything. Applied to a phase where you change the phase of where you change the face of 0 over here. Change the face of, okay, so in here you says you can change the face of everything except 0. The other way also works. There's two ways of performing the Grover diffusion operator. In this case, we're changing the face of everything other than 0. And so what this does is actually if we were to multiply the Hadamard into the zero bra, into the zero cat, the zero cat into the zero bra. I hope that you can see you do that. So when we apply it to the first term over here, what it does is basically gets two side bra. But when we apply it to the identity operator, the Hadamard gates cancel out. And so this is basically performing a reflection over the superposition of states. And this reflection, what it does is basically we can flip it over here. And I hope that you can see it's theta, because previously we were in O side. And now we're flipping over side. And so this actually gives us an increase in theta. And so what happens is that the probability of the good state increases now to sine 3 theta over 2. Okay. So does anyone have any trouble with this step? I see a comment. Okay, thanks, Diction. Okay, and so in this way, we can see that how the one Grover iteration works, which is to first flip the good state, increase it. Note that this no longer has a minus state, which is why you have to perform the oracle every single Grover iteration. Okay, and so from here, I'm going to need you to. I was planning to actually go through it a little bit, but I don't. In the interest of time, I'm going to need you to believe me, and this is homework for you all to do. But okay, in a better way, this is homework for you all to do it for yourself. I want you all to try performing the second, one more Grover iteration at home, in your own time, to perform one more Grover iteration and see what this increases to. Okay, I'm going to tell you the answer, which is for each Grover iterator, the amplitude of the state that we want to find increases by theta. And so after k iterations, the amplitude given for the good state is sine 2k plus 1 theta over 2. Okay, so okay. Yeah. Okay. So right now I'm going to need you all to believe me on this. I know I just proved it I just showed it for the first Grover iteration. I'm going to let you all just using the same logic, you can actually calculate this for the second Grover iteration, the third Grover iteration. So this homework at home is really meant for you to just kind of convince yourself that this is true, and that this is the amplitude given by this this is the amplitude given after applying a certain number of Grover iterators. Okay, as you can probably imagine, what this means is that there is optimum number of Grover iterators to apply. Why? Because after the amplitude, so sine will go from 0 to 1, then back down to 0, then to -1, then to 0 again. And so after a certain number of Grover iterators, where you kind of like go to 1, After it goes to 1, it'll go back down to 0. So you can't just apply as many Grover iterators as possible and hope that it just continue just increasing the state. At some point, applying too many Grover iterators would cause the amplitude to decrease as well. Okay, so now we just need to find the optimum number of times in order to increase to the amplitude of the good state to the highest amount. Okay, so the performance is to do with the complexity. Okay, so I went through this already. And so to do some math, basically, I typed out the math. I typed out the math here because I kind of figured that we might run out of time with the thing. I'm glad I did that. But basically, you want the value of k such that sine 2k plus 1 theta over 2 equals to 1. We know that this is basically pi over 2. We know that this is pi over 2, and that so after making k the subject of the equation, this is just pi over 2 theta minus 1 over 2. Using our favorite approximation in the world, which is basically because sine is a small because theta we are assuming theta is a small number over here, then theta over 2 equals to is basically 1 over square root 2. This is a very common approximation to make in physics. I hope you all can get by it. We can convert it into this form. K can get this form. Now, note that k has to be an integer. Why does k have to be an integer? Can anyone tell me? Yeah. Okay. So why does k have to be an integer? More specifically, k has to be a natural number. Yeah, because you are performing the Grover. Yeah, because it's the number of iterations. You can't have like 1.5 times the number of iterations. So k can't be a continuous value. And so we will define the integer value closest to k by k tilde. You perform and then you can get upper bound and lower bounds for it, and you realize that it's all basically bounded by square root n. So it's actually the upper bound that forms this O n bounds if you want to go into the actual mathematics of the big O notation. But I trust that y'all can believe me. I trust that y'all will believe me on this. Okay. So yeah, and so this is basically the entire idea behind Grover's algorithm. This is where the advantage comes from, because you're performing the Grover iterator O(n) times, and each time is kind of a constant because you're performing the same circuit over and over again. Okay, great. It's probably a good point to stop to ask whether there's any questions before I move on to the hands-on. Can we use quantum circuits to check if X satisfies Fx? Can quantum circuits circuit supports complex search conditions? Okay, so this is a very, very good question actually, and you kind of spotted one of the biggest problems with one of the biggest issues with Grovers from the start, which is what we started out with and why it's tough. Okay, so I'm going to go all the way back. What we started out with is this function, and we compared it to the classical unstructured search problem, which is basically unstructured search problem. And we are comparing O square n to On as if fx even though fx is for the classical unstructured search problem is going to be classical is the fx is going to be a classical form. This checking the specifications is going to be in classical form. We are the one of the main assumptions that we made is that we have the function f and that we can implement this in implement this in quantum circuits. To use and part of implementing this function in quantum circuits is just checking if x can satisfy fx, because I mean a big part of that is because this we'll get this answer out of it. So can quantum circuit supports these complex search conditions? It all boils down to this active area of research for Grover's algorithms and amplitude as for this amplitude amplification in general to create for smart ways of creating oracles. And so for it, can the question of can quantum circuits support complex search conditions really boils down to well, one, how unstructured your search problem is. In real life, you're really never going to encounter unstructured search problems as much. There's so going to be certain cases that I'll be mentioning later, where it's going to be similar to unstructured search problem. If you have complex structures that make it really difficult in the first place, that's where people are hoping Grovers might help. Because so instead of like when you have a structured search problem, generally your worst case complexity is not On. It usually goes down by a little. To something else, and so that's where things might happen. And so yeah, so just long story short, I think I started rambling a little bit. The question of can quantum circuits support on complex search conditions is an active area of research to do with how you want to create the oracle. And you are right in thinking that pointing out that the quantum circuits to check this is not necessarily kind of the same as the classical one. Does that answer your question? Is there a follow-up that you want to ask? Okay, thanks. Okay, great. Okay. If there are no further questions, I'm going to move on to the hands-on. Okay, so we are going to have to cut short a big part of the hands-on. So as usual, I would like you all to go to the GitHub. I would like you all to go to week 1, Grover's hands-on. There's Grover's the exercise, and I provided the solution as well. I hope you all try the exercise before you do the solution, but if you don't have time, you can just take a look at the solution. Okay, and so I did not download it yet, so I'll need to download it too. So for those of you with Git, I recommend please just download the Git as per normal. If not, you just follow what I'm doing. You just click the file, press download, and after it's downloaded, you create a new folder. Okay, someone needs to get link again. Dictionary, could you help post the link again? Over. And then um okay. Oh, here. Okay. So Okay, so I there are two parts of the exercise. One is I want you all to start to think about how to try solve to try to solve a function that to solve basically uh to find the element 100 in the domain of 0 to 7. I'm asked you all to build. So I know that this is kind of a trivial example because one, we know the element already. We are kind of creating artificial problem for us to solve. We are building the oracle ourselves, and this does not actually really create a proper way of a proper robust unstructured search problem, but it's the simplest one that I could think of. I ask you to build the diffusion operator, and I ask you to implement the Grover circuit. So, but before we do that, I think it will be helpful if we go through the circuit on the whiteboard first. Okay. So, Dikshan, could you help me? Okay. So great. Okay. So okay. So the problem that we want to find that I'm going to define right now is that we have this domain 0, 0. We have this domain which 0, 1, 1. 0, 1, 0. Okay. So we have this domain. This domain of eight. Yeah, eight elements. I hope that you can see this basically corresponds to 1, 0, 1, 2, 3, 4, 5, 6, 7. This is just binary, and this is decimal. Okay, so this is the domain we want to work with. Okay, so this is the domain that we want to work with. And so let's say we want to find 100 as we did inside the thing. So right now we are kind of constructing the oracle. Generally, we assume the oracle is given, but because we are kind of like defining an artificial problem right now, then we are going to learn how to construct an oracle. This will be the reason why I wanted to go through this was because it's constructing the oracle for a non-specific function generally requires similar techniques. So is this okay? So as you can tell, this would definitely require 3 qubits to start with. This requires 3 qubits to start with. And what we want to do, okay, so the Grover circuit, the first thing you do is obviously you apply the Hadamard gate. And so with the Hadamard gate, so step one is the Hadamard gate. Uh, Step one is the Hadamard gate. What do you get when you apply the Hadamard gate to everything? Can anyone answer? What happens when we apply the Hadamard gate to 3 qubits? goes to the positive. Sorry, I don't really understand that. What happens when we apply the Hadamard gate to for on just a zero? Yeah, they all go to yeah, okay. Oh yes, they go to the plus state. Yes, it does. Okay, so they all go to the plus state. They all go to the plus state, which is correct. They all go to the plus state. And but what this also does, I think a more useful representation for this is that this would be it will be the uniform superposition of all these states. Okay, so step one does this. Okay, so step two is the Grover iterators. And so Grover iterator, which is basically I'm going to separate it to 2.1, which is Oracle, and 2.2, which is diffusion operator. And 2.3, I'm just going to say n square root n times. Okay. So step 2.1 is the Oracle, which we are going to learn how to implement. Okay, so what if we want to find 0, 1, 1? This if we want to find if we want to find 1, 0, 0, right? What do I need to change to this? What does this Oracle function need to change to this function over here, to this uniform superposition of states here? What does the and remember in the intuition, what does the oracle do? It marks the good states by flipping the face, correct? So the end goal for the oracle would basically to get okay, I'm placing that to 0, 1, 1 minus 1, 0, 0. Okay, so this is what we want the oracle to do. We just learned how to do something like this this morning. What did we do? Okay. Mhm. What did we do this morning in order to fit the face of things? You can just say the name of the technique that I taught you all this morning. What's the name of the technique? Does anyone remember? You all don't have to give me the. Uh, you also remember what we did over uh, thing. Over here? What is this technique called? Uh, Okay, I can't tell whether your yes, face came back. Uh, do y'all remember do y'all remember the face kickback, or is it still just kind of a blur to y'all? I'm just trying to get a sense of the situation here. Okay. Yeah. So anyway, the technique that we used was something it was face kickback, which basically which is where the Oracle workspace that you see in the circuit inside the slides came from. So you have your first register, which you already applied the harder mark to. So this is the first register. One way of creating face flip, the face flip is basically to do something similar to what we did over here for the oracle. So if we want to create the oracle, so to create the oracle for this, one way to do it is to, for example, just put the one state and have a tree multi-control gate over here. And this flips for Z. Okay. What state does this flip? What state does this multi-control gate flip over here? When I ask what state, so there are 8 answers to choose from over here. Which one do you think this multi-control gate flips? It only flips one of them. 110? Or there's 3 over here. It's no longer the two qubit one. Yeah. Okay. So it flips this one flips the 111 state. Okay. And so what we have to do is now, because we want to instead flip, we don't want to flip the 111 state. We instead want to flip the 100 state, basically. Right. And so what we have to do is we basically have to change things in a smart way in order to we have to change this circuit in a smart way by using bit flip operations. So can you see that if 110 comes if what we want is that we want to apply basically something over here, this part, that when 110 comes in, it changes to 111, while everything else changes away from 111. While everything else changes away from 111, it will become, and then we perform this, and then we change things back later from 111 to 100. How we do this is we apply the bit flip operator. So what we do is we apply, we don't do anything to the first one. We do apply the X gate to the second one, and we apply X gate to the third one. Then we perform this control, and then we flip it back. Okay, and so with this, I hope you can see that from here, if we start at 111 100, over here, the state 1, 0, 0. In this part, it changes to 1, 1, 1. Over here, it changes, oh, sorry. Over here, it becomes minus 1, 1, 1. And over here, we go back to 1, 0. We go back to 1, 0, 0. And everything else would just also change with it. So none of this would kind of remain. This when we apply the x to this one, it'll become 0, 1, 1. Apply to this one, 1, 0, 1. This one will be 0, 1, 0, 0, 1, 0. And if you do the rest, you realize that there's only 1, 1, 1 left. Okay. And so this is the way that we can perform the phase. One of the ways that we can construct the oracle. Now, the phase kickback is a really strong technique because you can do this. If let's say I could even change this to minus state and perform the I could change and perform the control. Instead, perform the multi-control qubit gate over here. But a big part of Oracle design is actually thinking about ways that you can reduce the number of qubits you use and reduce the number of circuits you use. Generally, a 2-qubit gate is going to be less expensive than a 3-qubit gate. A 3-qubit gate is going to be less expensive than a 4-qubit gate. For this particular case, there is a smart way to apply this. There's a smart way to apply another operator in order to create OR, and that is the control Z gate over here. Okay, I'm going to put the X over here. Now, why the phase kickback is really strong because there is a very systematic way to do things. This is a very, very systematic way. You can do this without a problem for almost anything, for almost any problem. This one is very specific to this current problem that we are trying to solve. You notice that when we apply the CCZ to it, so what the CCZ, so we can define it by the different states that it applies on. So we are just looking at this particular function at this point. Okay, I'm going to speed up slightly because we're running out of time. Now, when we apply the CCZ over here, I hope you can see that CCZ, nothing happens for these six states. Nothing happens because they all have zeros in the first 2 qubits. I hope you all can see that. So this all remains the same. Now, the question is, what happens for the other 2 qubits, for the other 2 states over here? 0, 0, 1, 1. So we apply the Z gate to 0. What happens when we apply the Z gate to the to 0 cat? Nothing happens, right? Because the Z is basically 1, 0 minus 1 is right. Nothing happens when we apply 0. And so this remains 1, 1, 0. And this one becomes to minus 1, 1. Okay, which is exactly the same thing that happened for this part. For this part over here. Okay, so with phase kickback, I introduced a systematic way of doing it. And then for this one, I introduced a very problem-specific way of doing it. I'm hoping that that gives you an idea of the nuance behind the different Oracle designs that come. The next part is the diffusion. The next part is the diffusion operator. Okay, so yeah. So for the diffusion operator, uh, what you need to do, if you remember the circuit, is basically Hadamard, 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 change something, and Hadamard, Hadamard, Hadamard. Okay. In the interest of time, I'm just going to give you all the answer, which is basically you will want to basically perform the you basically want to perform instead to change the phase of 0, 0, 0 rather than okay, so inside the PowerPoint, you want to change the phase of everything other than 0, 0, 0. I'm just going to tell you right here is equivalent to just change the phase of 0, 0, 0 and not change the phase of anything else. So in the slides, you basically this function basically performs 0, 0, 0 to 0, 0, 0 and everything else. So 0, 0, 1 to minus 0, 0, 1. 0, 1, 0 to minus 0, 1, 0 dot 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 all the way to 1, 1, 1. Okay, so in the slides, this is what it does. Equivalently, what we can do for Grovers is we can also just apply this, and the rest remains the same. And the rest remains the same. Okay, so this is two ways of building the diffusion operator actually. And I hope that you can see that with this, right? This is basically the same problem as this problem that we went through over here. Except instead of performing the X on just the first two, we perform the X on all three. Okay? And so this basically, what you have here is basically X, 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 CZ, X, X, X. Okay. And the last thing is to just calculate the number of times to apply it. Which you already have the upper bound for. You already know the equation because it's just basically the pi over 4 equation. And so I'll let you figure that out, and I'll kind of let you figure that out. For this particular case, doing it once is enough. Okay, so with that, I'm just going to show you all the solution to the hands-on. I show you all show you all the solution to the hands-on. So this is the solution so here we implemented CCZ. We create the 100 oracle, which is exactly in that circuit that I showed you. We did the X gate to the first two, the second two, and then we do the CCZ. Then we perform the X gate again to flip it back. We built the phase change. Then we built the 0, 0, 0 phase change. For the phase change, we apply X on all of them, and then we apply the CCZ. The diffusion operator is then basically for 3 qubits is basically performing Hadamard, then adding this circuit, and then performing here. And so with this, we have our oracle, and then we have our diffusion operator. And so to build the Grover circuit, what we do is we just Hadamard everything. We declare our Oracle amplification, and for each iteration over here, we do Oracle circuit and amplification circuit, and then we can calculate the probability of it. Okay, so over here, okay, and so with this circuit, you can see this is exactly what I've showed just now. We can run it, and we can see that increases the amplitude over here. Okay, so right now I put iterations count equals to 2. We can see 1. I think I remember wrongly. Yeah, the maximum one is probably, yeah, the maximum one is probably 2, not 1. But yeah, it's close. So if you apply the Grover iterator once, it comes to this. If you apply the Grover iterator twice, increases slightly. And then if we go to 3 times, it worsens. So it's very important to get the number of Grover iterators correct in order to maximize your amplitude. And you can see that just implying it one extra time can actually decrease the probability of finding it by quite a lot. Previously, it was like nearly 90%. Now it's only like 30% of measuring it. Okay, so yeah, so I also asked you all to generalize the simple case as an exercise to do the oracle. I provided the solution for it as well, but I hope you all can try it in your own free time. Okay, so the last part, which is I think I went through. Okay, did I stop sharing here? Okay, so the last part of the lecture, I'm going to rush through the last part of the lecture for another couple more minutes. So there's a huge, I think I intimated this previously with one of the questions, is that there is a huge problem with Grovers. And that is assuming that we know how to implement the Oracle. This is a non-trivial problem. This is a problem that this is a very active area of research because creating the Oracle is not easy. This is something that we've known for a very long time. But last year, this very interesting paper came up that comes out that he kind of came and says like Grover's algorithm offers no quantum advantage. Long story short, actually, that I wanted to tell a couple of anecdotes around it. This was a really controversial paper. It generated a lot of discussion because it's like, this well-known fact of like Grover offering a quadratic advantage this year. I think some people were basically amazed that it even passed through peer review. Some people were, and some people were like, you're not talking about anything new. Long story short of it was that their wording was very misleading. And they admitted that Grover can still provide the quadratic advantage. But their main argument over here is that when push comes to shove, in terms of creating the quantum oracle, and for the quantum oracle, which this is a problem that we knew 20 years. So one of the comments against this paper was like, please take a look at this textbook from 20 years ago. We already knew about the problems you're talking about. The fallout was kind of funny to watch out to look at. But the main problem is that quantum oracles are hard. The problem with it is that once you know how to create a quantum oracle, and in order to implement the quantum oracle in the first place, you are going to know the circuit that implements a quantum oracle. And what you can do, in fact, is actually you can see whether you can take that circuit, you can take the matrix that the circuit forms, and see whether you can implement it classically. You can see whether you can find a smart way to use that matrix classically, because that is information that the circuit technically knows now. It has been shown pretty conclusively that for unstructured search problems where you don't for so for example for this particular case that I went through, if you know the circuit for the oracle, sorry, if you know the circuit for the oracle, you can kind of like use that. So you can use the circuit to find the 100 without even going through that entire problem. Okay, so yeah, and so they there are a lot of issues with it. And but it has been shown that you can use it for generally for unstructured problems. What type of unstructured problems can you use it for? Okay, so in this lecture, I've talked about grovers in the form of the unstructured search problem. Grovers can be used for a lot more. And in fact, uh it's not Grover's algorithm that is important. It's not this unstructured search problem that is important. It's in fact this entire iterator. This The importance of Grover completely lies in the fact that this technique that it proposes for speed ups. And this is something that I think Pascal mentioned just now. This is something we call the amplitude amplification technique, which is basically to flip the good state and then flip around the face. Flip the face around the uniform superposition state. This amplitude amplification technique is the one that helps to provide a quadratic advantage for a lot of different problems. And you can use it for Grover's algorithm, which is used for unstructured data-based search. You can use it for quantum counting. You can use it for another algorithm called quantum amplitude estimation for quantum Monte Carlo for other users. For quantum amplitude estimation, you can actually also use it for set problems, satisfiability problems. In fact, there's been a well-known argument among the scientists about the tree set problems, because the tree set problem is basically a structured satisfiability problem that the Grover can solve in the Grovers can solve in basically square root n, but which is basically kind of like 1.414 in some I think you can solve it in basically O n to the power of 1.414, which is square root 2 square root 2 on something like that on top. But the best classical way is OX 1 to the power of 3 1, I think. And so there was some very interesting arguments, some very interesting discussion around that. One of the satisfiability problems that QAE can be used for is something called circuit set, because circuit set is almost completely unstructured. QAE has been proposed for many different things. In finance, for derivatives pricings, you can see pricing of derivative functions. QAE has been used for solving different mathematical and physical equations, over here chemical equations, and it's also been proposed for machine learning and for quantum activation networks for anomaly detection. These are all examples of things that QAE might be used for.